Okay, let's now consider the third type, that is RadFrac column. Here I have opened the third file that I have saved earlier for the current Aspen Plus simulation project. Now we will select the columns tab in Model Palette that you can see here and place a RadFrac column into the process flowsheet window. Then we will connect the product stream exiting the third mixer to the RadFrac column and add the two product streams where Aspen Plus indicates they are required. And also we will add a third product stream off the condenser to account for any free water that can be separated from within the condenser. So let's do that. Okay, so now click on the RadFrac icon, then place your column here. Then right-click inside the main flowsheet window to cancel the insertion mode. Now I'm going to resize the column like this and rename it RadFrac 1. Place the tag here and change the location for this column. Now I'm going to hook this stream here to the column. So right-click on it, reconnect destination, and then I will click here on the red arrow to connect this stream to the column. Okay, now let's add the product streams to this column. Click here on the material icon, then bring your mouse inside the main flowsheet window. And as you can see here, we have several arrows where we can put our products. Remember, the red arrow indicates that the stream is mandatory, and the blue arrow indicates that the stream is an option. So for the bottom stream, which is here, click on the red arrow, then left click again. And for the top stream, click on the red arrow, then left click again. And now we will add a third product stream off the condenser that you can see here to account for any free water that can be separated from within the condenser. So bring your mouse on top of the blue arrow, click on it, then click here again. Now right-click inside the main flowsheet window to cancel the insertion mode. Now I'm going to rename and resize my streams. So for the bottom one, I will call it Red BTM. For the top one, Red Top. And for this one here, Red H2O. Okay, notice now that the simulation status changed to required input incomplete following the addition of the new distillation column. Now click on the reset button. Now click on the next button, and this will bring you to the input tab for the new distilling column. As you can see here, RadFrac column requires more input than either the DSTWU or DISTL column. For example, this column model requires us to enter the number of theoretical stages that you can see here, as well as the reflux ratio. Now, in this simulation, we're not going to use the preliminary results from the previous videos, but we will use a different set of operating parameters. So, for the number of stages, you can type in 10. For the condenser, you can keep the default setting total. For the reboiler, kettle. And here for the valid phases, make sure you select vapor liquid free water condenser. Remember, we have added a third product stream off the condenser to account for any free water product that can be separated from within the condenser. For convergence, you can keep standard. And here for the operating specifications, click here to expand the list, select distillate to feed ratio, and type in here 0.95. Then for the reflux ratio, you can type in here 2. Remember, the reflux ratio that we have determined in the previous video was about 1.4, but in this simulation we will put 2. Now, once you have done this, click on the button Feed Basis. Here, basically, you need to tell Aspen Plus what the feed basis is and what component is to be used for the distillate to feed ratio that we have specified here. In our case, our column is fed by the stream exiting the third mixer, so our feed is this one. So select it. Then the component to be used for distillate to feed ratio is acetone, so select acetone. Then click on the Close button. Now, as you can see here, we have a blue check mark next to Configuration. But notice that we have still 2 tabs to be filled in, and these are Streams and Pressure. So click on the Streams tab. Here, we need to input the location of the feed stream. As a first approach, we will locate the feed at the middle stage of the column. So type in here 5. And this completes the Streams tab input. You can see here a blue check mark next to it. Now notice here, in this level here, that the tray corresponding to each product stream is shown in this window. So, for example, the bottom stream is at stage number 10, and the top stream is at the first stage. Now, if we have any side stream from our tower or an additional feed, we will need to input the tray that it issues from or merges to, and it should appear here in this tab window. Okay, let's now move on and complete the data for the pressure tab. For the purpose of our simulation, we will simulate a distillation column that is operating at 0.8 bar with a pressure drop of 5 millibar per stage. Notice here that Aspen Plus gives us the possibility to specify the pressure of the second stage, as you can see here, or to specify a pressure drop for the column, whether per stage or for all the column. In real operations, there exists a pressure drop along the column from the bottom, which represents the highest pressure, to the top, so the lowest pressure, and this is accounted for here in Aspen Plus via specifying either a stage pressure or column pressure drop. So let's input this as the operating pressure for our case. So here our column is operating at 0.8 bar, and we have a stage pressure drop of 5 millibar. Okay, now we have entered and specified all the required input parameters, and as you can see here, you have blue check marks next to each tab. In addition, the simulation status has now changed to required input complete, indicating that Aspen Plus has now all the data to complete the simulation. So go to the Home ribbon, reset the simulator, then click on the Run button to run the simulation. Now let's view our results. So click here on the Stream Summary button. Now let me scroll down to the mass fractions and then see the composition of our top stream that you can see here. So notice that we did not meet the required purity we are looking for of 0.95, and the top stream yields 94% weight acetone. Actually, we're not that far. With some adjustment to our input parameters, we can easily achieve our goal. But what I want you to understand here and to keep in mind is that the ability to split a feed stream into almost 1 or 2 pure streams depends on many input parameters, as you can see here. For example, increasing both the number of trays and reflux ratio will grant us more luxury to have a higher degree of separation. So let's increase the number of stages to 24 and the reflux ratio to 3.5 and then rerun our simulation. To do that, go to RadFrac, Specifications, Setup, then change this from 10 to 24 and the reflux ratio that you can see here from 2 to 3.5. Then go to the Home ribbon, reset the simulation, and then rerun it again. And let's now check the new results. So let me scroll down and look for mass fraction. And then this stream here is the top stream of our distillation column. Now the new weight fraction of acetone in this stream is now 97%. And as you can see, increasing the number of stages and the reflux ratio gave us more luxury to have a higher degree of separation, and the acetone weight fraction jumped from 94% to 97%. Okay, let's now look at the results for the RadFrac distillation tower. To do that, go to the navigation pane and select the appropriate unit operation under blocks. So here you have blocks, then scroll down until you see the EO modeling subfolder, and then click on the results file. This window shows the final operating conditions for the distillation column that were calculated by Aspen Plus. You can see in this window that the molar reflux ratio is 3.5. You can also see the required condenser cooling duty, which is in our case here, if I change it to kilowatt, equal to minus 31.62 kilowatt. Of course, the negative sign here indicates that heat will be taken off the condenser. On the other hand, the reboiler bottom stage performance table that you can see here, immediately below the condenser table, gives the required heat added to the reboiler, which is, in our case here, if expressed in kilowatt, equal to 35.49. Now, if you select the Balance tab at the top of the screen, you can see here the overall heat and material balances for the column. You can also see the relative difference in the values, indicating that no simulation is 100% perfect. Finally, under the Profiles sheet of RadFrac block that you can see here, Aspen Plus presents a summary of the operating conditions for this simulation. Under the TPFQ tab, you can see a breakdown of the liquid and vapor flow rates from each column tray. From the View drop-down list, you may select all or a subset of profile results, such as summary, feed and products, stage flows, and heat duty or enthalpy profile. And now, under the Composition tab on top of the screen, you can see here the profile of each of the components throughout the column. Now, finally, to finish off this video, it is worth mentioning here that since we have in hand a rigorous column model, a design specification case study can be conducted here, where the design specs variable will be the mass fraction of acetone in the top stream with a target value of 0.95 and a tolerance value of 0.001, and the manipulated variable will be the block variable, so namely the reflux ratio. So as an exercise for you, try to run this sensitivity analysis with the figures that you can see here, Then check the results and compare them with our initial simulation. Recall, we have covered the design specification feature of Aspen Plus in a previous video, where we carried out a sensitivity analysis and examined how the flow rate of MIBK impacts the purity of acetone exiting flash 2 in our process diagram.